Standard software relies on predictable pipelines. Give an input, execute business logic, and deliver an output. Early LLM applications mirrored this linear chain. Feed a prompt, wait for a response, and output the result. This works for generating an email, but more complex requests strain the linear path. Researching a live market trend, summarizing the findings, and formatting a final report requires several distinct interlocking steps. A linear chain lacks the mechanics to step back. If the LLM hallucinates early on, it breaks the pipeline. The system cannot evaluate its own work, pause for missing context, or retry a failed step. An autonomous AI agent requires different behaviors. It must reason about a request, search for external information, remember previous results, and decide its own next step based on changing conditions. LangGraph is a framework within the LangChain ecosystem designed to solve this architectural bottleneck. It discards the linear pipeline in favor of a graph-based architecture. Developing in this framework means organizing logic around three core primitives: state, nodes, and edges. This stateful, highly controllable graph architecture provides the structural foundation required to build a fully functioning AI agent. In a graph architecture, everything centers on state, the shared memory. Instead of passing variables directly, every part reads from and writes back to this center. Surrounding this are nodes, independent workers. Each node receives the state, performs its job, and returns an update. Once a node completes its task, the graph determines where to go next via an edge. Edges enable conditional routing. This logic allows the application to evaluate the live state and dynamically select the next node, bypassing hard-coded sequences. This enables the system to loop back to a previous step to correct an error or bypass nodes that are no longer necessary. By decoupling execution from a fixed sequence, these three primitives provide the mechanics for autonomous decision-making. An LLM is limited by its training data. It can only generate and interpret text. Tools provide the mechanism for agents to interact with external systems and perform actions in the real world. Consider a request to find and summarize the latest Java developer jobs matching a specific profile. The graph routes this request to a node equipped with an external API search tool. The API retrieves live job data, pushing it directly into central state memory. Because the state now contains the search results, conditional routing sends that data to a final node for summarization. The LLM acts as an orchestrator for this multi-step workflow. Combining nodes, edges, and tools allows developers to build complex execution topologies. The reflection pattern, for example, is used to implement self-correction. In this pattern, an initial output routes to an evaluate node instead of the user. If it detects a failure, an edge conditionally routes the process back for improvement. In operations involving financial transactions or compliance, AI should not operate with total autonomy. These scenarios strictly require a human-in-the-loop workflow. The state pauses at a hard stop, waiting for an external human authorization before the edge allows the process to proceed. These graph configurations establish self-correcting, auditable processes. Using one monolithic agent to handle every task in a large system creates significant operational risk. Multi-agent systems manage this by dividing responsibilities and isolating risk. A master routing node delegates subtasks to distinct, smaller graphs. These specialized agents operate under strict constraints, each having unique instructions and restricted tool access. Once a specialized agent completes its task, it returns the result to the master workflow. This separation of concerns makes large-scale operations easier to govern and troubleshoot. As workflows grow in complexity, multi-agent architecture ensures their execution remains bounded and manageable. A local demo agent is a far cry from a production-grade deployment. Production requires durable execution. State must persist across workflows that might span hours or days while waiting for external updates. Granting autonomous tool access to LLMs without oversight introduces serious operational risks. A complete agent graph must be wrapped in protective layers. These include role-based access controls, strict tool permissions, and prompt injection defenses. Observability is also critical for monitoring distributed tracing, token consumption, and failure points. This architecture often integrates with mature platforms. We can see a clear separation between an intelligent orchestration layer and a lower business capabilities layer. Existing microservices in Java or Spring Boot remain responsible for core business logic, while the agent layer provides the orchestration. LLMs provide intelligence, tools provide capabilities, state provides context, LangGraph provides the orchestration that binds these elements together, allowing AI to function as scalable enterprise software.